Welcome back to Chemistry 131A. Today we're going to talk about particles, waves, the uncertainty principle, and some of the postulates of quantum mechanics. As you recall from the last lecture, we found out at the turn of the last century, by which I mean around 1900, that in fact particles were behaving strangely and classical physics was not accounting for all the observations. And so a new theory was put forward, which came forward over a period of time, called quantum mechanics. And like any fundamental theory, it has to be compared with experiment. And so there were experiments that were done. We saw some more modern experiments last time in which an electron in an electron microscope behaved very much like a wave, the experiment of Tanimura at Hitachi. And in fact, this wave behavior had been observed and caused Louis de Broglie, I believe it's actually pronounced de Broglie, but just to keep it clear, we'll say de Broglie anyway. He proposed in 1924, in fact, that all particles have an associated wavelength that is related to their momentum, and that this wavelength just follows the same relationship as that for a photon. We saw last time that the photon momentum was given by h over lambda. And de Broglie proposed that, in fact, there was a wavelength, then lambda, that was related to h upon p for a particle, not just for a photon. And in fact, in 1927, 3 years later, Davison and Germer showed that an electron beam fired at a nickel crystal showed a diffraction pattern. And that's a wave phenomenon. And furthermore, they looked at what the wavelength of these electrons in the beam would have to be. And the wavelength was very, very close to the exact prediction that de Broglie made. So the question is, where is the particle? In classical mechanics, the center of mass of a particle has, in principle at least, an exact location at all times. In quantum mechanics, it's not quite so clear. In classical mechanics, the particle follows a trajectory. What a trajectory is it's an exact specification of the position of the particle and the momentum of the particle, or its velocity if the mass doesn't change, at all times. And that's in fact how we do all kinds of calculations in classical mechanics, whether I'm going to shoot a shell and have it land somewhere or anything along those lines. And that works extremely well for large objects. But it fails for small objects because they show this strange wave behavior. Now, the problem with something that's demonstrating a wave-like behavior is that we can't say for certain where a wave is, because waves tend to spread out over time. And so we're kind of caught in a little bit of a difficulty, because if we can't actually say where the center of mass of the particle is, if it appears to be blurry, we can't specify it exactly. That means that we can't have a trajectory. And the trajectory, following Newton's laws, is exactly how you calculate where things are going to end up. And so now you've got to have a new method to calculate how things are going to behave if they're showing this wave-like phenomenon. And so that was a big chore, actually, and took a lot of very smart people a very long time to work out. In 1927, Werner Heisenberg made this blurriness more formal in the famous uncertainty principle, which states that no matter how you design an experiment, it is impossible to measure the momentum and position of a particle with arbitrary accuracy. There is a certain minimum amount of uncertainty that's left over, given in this famous expression delta p delta x is greater than or equal to h bar over 2. it's important to emphasize that this has nothing to do with your experimental apparatus having some sort of deficiency. This is just an idealized experiment done as best as you could possibly do in this universe, and you still cannot simultaneously specify the two things at once. In fact, the quantity h over 2 pi occurs so often that we invented a shorthand notation called h bar, h with a slash, or h cross was created for it, and you'll see that often in the formulas that we use because we get tired of writing 2 pi so much. The uncertainty principle says that we just cannot simultaneously determine position and momentum to arbitrary accuracy, no matter what we do, even in an idealized experiment. And that runs counter to our everyday experience, where we seem to be able to watch a rolling marble and plot its mass and figure out where it is basically about as well as we want to. And so there must be something in this thing that makes it different for small particles. And the something is the exact size of h bar. If h bar were bigger, we would notice all these things happening with big objects, but h bar is so small that we don't notice it the same way we don't really notice the momentum of a photon. Otherwise, the lighting that is on me now would be pushing me around, and I'd have to fight like a mime to keep my position. Now, the rationale is when we think of looking at something, we're looking at something with the lights on. We can't look at something in the dead pitch black and see anything. But if you've got a small particle, then we've learned that light consists of packets, photons, and these have momentum and energy. And so when we try to see where a very small particle is, we can't just look at it. We have to bounce something off it. We have to use something like light. And the light itself is going to change the momentum of the particle. And if we want to get the position to be very close, then we have to use a short wavelength of light. But that's a high frequency, and we learned that the quantum energy of light is h nu. And so if nu is high, that means that we're going to come in with a ton of energy, like an X-ray, and then that's going to boot the particle around. And so although we could say it just was there, now we can't say very well what its momentum is. And these ricochets happen all the time, and so we have a fundamental problem if we try to do it. Now, if we turn off all the lights, then we know that the particle is moving with a certain speed, but then, of course, we can't tell at all where it is. So for small objects, the photon kicks the particle, and that creates the fundamental problem. So if we don't really know how big an electron is, it appears to be a point if you do experiments with it. But to tell where it is, we need then a wavelength of light that's small. So just the same way if you put on infrared goggles and you look at night, you can see heat, but everything's much blurrier because it's not as sharp as visible light because it has a longer wavelength. So we need a small wavelength of light to get a particle down to what we would consider to be a reasonable precision of measurement, and that gives a big kick to something like the electron and knocks it. And so the electron momentum in that case becomes very uncertain. Conversely, you can think of how you might design an experiment that would measure the momentum of a particle. One way to do it would be to have a very, very long, thin tube and have particles coming in, and if they aren't going straight along the tube, then they hit the wall and they're out of there. And you can have some choppers like fan blades at certain distances and moving with certain rotational speed. And if the particle happens to be going the right speed, so it goes through the whole of this fan and then the whole of that fan and so on, then you know for sure that it has a momentum within a certain range. So you've isolated it very well. But if you really want to get it to be very, very small uncertainty, that means you're going to have a very, very, very long tube. And then the particle could be anywhere inside the tube. So you don't really know its position. And of course, if you open it up so it's not dark and you put light in, then that fouls up the momentum, as we said before. So we can't specify the position of any kind of object without light to see it, or something else, which would be even worse, probably. Now, for macroscopic objects, the uncertainty principle does not limit us. We're always limited experimentally for anything we do that's of size we can see. It has nothing to do with that. But for very small objects, like a single electron, it becomes the major factor. So here's a practice problem that's meant to illustrate this difference. Suppose so practice problem 3, suppose we take a 1 gram marble and we know its position to 1/10 of a millimeter, which is pretty good. And we know the position of an electron to 200 picometers, which is 200 times 10 to the minus 12th meters. The question is, what would be the minimum uncertainty according to the uncertainty principle for the velocity in each of these cases? So first of all, the uncertainty in momentum is in the velocity, not in the mass. The mass stays fixed, so delta p becomes m delta x. And then we use the uncertainty principle. Delta p delta x is greater than or equal to h over 4 pi. We have to be a little bit careful with the units. We were given the units in grams, but we have to convert to kilograms. And we were given the uncertainty in millimeters, but we have to convert to meters because we're using MKS units. And if we take account of all those factors, then we find that delta V is h, which is 6.62 times 10 to the minus 34 over 4 pi. And then we have 10 to the minus 3 kilograms, that's our 1 gram, and 10 to the minus 4 meters. And if we work out the units carefully, we find that the uncertainty in velocity is 5.2 times 10 to the minus 28 meters per second. For reference, an atom is about 10 to the minus 10 meters. And so the uncertainty in velocity is way, 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 way smaller than anything we could possibly ever notice. So it's just as good as almost infinite precision as far as we're concerned. For the electron, however, if we do the same calculation, and here the difference is, we put in 9.1 times 10 to the minus 31 kilograms, and then we put in 200 times 10 to the minus 12 meters, then what we find is that the uncertainty in velocity is about 2.9 times 10 to the plus 5 meters per second. So that's 200,000 meters per second. If you've ever run a 10K, you realize that that's running pretty fast. And so trying to localize the electron down to just 200 picometers means that its velocity becomes very, very uncertain. So the uncertainty in velocity is very, very large in that case. And the reason why there's a large uncertainty for the case of the electron is that the electron has such small mass, whereas macroscopic objects in the 1 gram range, there's no problem. Okay. Now, de Broglie said, look, matter has a wave associated with it, which is kind of a semantic dodge. It's not as if matter has suddenly become a wave. we still can detect particles in the Tanimura experiment. When they hit the screen, they give a dot. And we know how to characterize a wave. There's a phase, there's a frequency, there's an amplitude. And in fact, wave equations were known from electromagnetic radiation, Maxwell's equations, which seemed to indicate that light was a wave and explained many of its properties, was a wave equation. And so physicists knew how to write those things down. But there's kind of a question here as to whether this associated wave is a real thing or not a real thing. Is it a calculational device or is it a real thing? Well, Davison and Germer seem to indicate that it is a real thing, that this de Broglie wavelength for small particles, this can be the main thing depending on what kind of measurement you're making. So the question is the de Broglie wavelength an actual measurable thing? And if it is, then what equation do we write for the wave? And finally, if the behavior is wave-like, then how do we explain the sharp spots in the Tanimura experiment? When we wanted the electron to sift through both of the slits, it was convenient then to think of it like a wave, because a wave can do that and a particle cannot. But when it hits the detector, it seems like it collapses like a poorly rigged camping tent onto just a single point on the detector. And it certainly doesn't light up the detector like a wavy thing. We see these sharp spots, and only after we measure a lot of these measurements do we in fact see that the aggregate behavior is wave-like. Each individual one doesn't look wave-like. So this took a lot of thought to sort out, for sure. We don't notice any wave-like behavior with macroscopic objects. We don't notice any, when we move around, we don't notice that there are waves coming off my hands or that I can't tell where my fingers are or anything like that. And the reason why is the same reason as with the marble. The small value of Planck's constant is the explanation. We're just so much bigger than h bar that we don't notice that. And for an illustration, let's do another practice problem 4. Well, let's figure out the de Broglie wavelength of, first, a 5 milligram grain of sand moving at 0.1 centimeters per second, blowing along the beach, and 2, an electron moving at 1 kilometer per second. Well, for the grain of sand, we just plug into the de Broglie wavelength formula. Lambda is h upon p. And then the rest of it is what a lot of chemistry is. It's units conversion, keeping track of the units, crossing them all out, and making darn sure at the end that the units are what you intend to be. So in this case, I explicitly wrote out a joule is a kilogram meter squared per second squared. Cross out the joules, cross out the kilograms, make sure the milligrams is turned into kilograms, make sure the centimeter is turned into meters, and I find that the de Broglie wavelength for the grain of sand is about 1.3 times 10 to the minus 25 meters. That means the associated wavelength is much smaller than any nominal size we would think of a grain of sand, which is certainly much bigger than an atom. However, for the case of the electron, the de Broglie wavelength, working out the same math, but using the electron mass and using the velocity given, now converting kilometers to meters, it works out to 7.3 times 10 to the minus 7 meters. An atom is 10 to the minus 10 meters. And so now we're talking about a wavelength of the electron moving at this speed that's much bigger than anything we would think of as the size of the electron, because even if we don't know exactly what the size of the electron is, we know that atoms have electrons in them, and therefore the size of the electron has to be much smaller than the size of the atom, or they'd be like beach balls and they wouldn't fit. And so in this case, when we have this situation, when the wavelength that we figure out from the de Broglie formula is in fact much bigger than any nominal size of whatever it is we're considering, at that point we have to say, watch out, because whatever this thing is, it could surely show quantum behavior. When the de Broglie wavelength is very much smaller than the size of the thing, our idea of the size of the thing, then we aren't going to see any kind of wave behavior, and we might as well just cut to the chase and use classical mechanics to figure out what's going to happen. So that's summarized in this next bullet point. We don't notice any wave behavior if the particle has a very small de Broglie wavelength, and if it's larger, then we surely do notice it. At least in some experiments, we will. Now, what are we going to use to actually figure out what something's doing? For particles, we had Newton's laws, we had ways of figuring out F equals ma and so forth, what was going to happen. Now we have this de Broglie wavelength, but we still don't have a wave. And we don't really want to call the particle a wave because that's a little bit confusing. It makes you wonder what a particle ever was. And so what we do is we have kind of a little bit of a dodge. We speak of the wave function of a particle, and the wave function is associated with it, and it's given the symbol psi to describe its behavior. And whenever chemists want to keep out people, they switch to Greek letters, because if you switch to Greek letters, then it seems much, much more intimidating, and you have job security. But the symbol psi is universally interpreted as a probability amplitude, and I'll get to that in a minute. And the absolute square, if we square it, we get a probability density. And there's a reason why we're using probability and not certainty, and that part of that has to do with uncertainty, and part of it has to do with the very nature of measurement, as we'll see in the end of this lecture, possibly in the beginning of the next lecture. We can only know, quantum mechanics says, the probability, not the certainty, even as frustrating as that might seem, of finding the particle somewhere. Due to its wave nature, it appears to be spread out. And when we measure it, we interfere with it somehow, and that causes the measurement to collapse, like the tent I mentioned. But the probability is uncertain until we finally make the measurement. It's as if I take a die and I throw it, and I'm not looking at it. And then it lands and it bounces and it rolls around and so forth. And then I look at it and it's a 2. And I said, well, the probability beforehand of getting a 2 was 1/6. But in fact, now that I see it's 2, the probability is 100%. And we're going to see that phenomenon when we make a measurement. Once we know, then all the other possibilities seem to have just vanished somehow, which is a little bit mysterious, but that appears to be what happens, and that's a common interpretation anyway of the theory. Once we measure the position, we can yield different values, and even though we have exactly the same electrons coming through the two slits, and everything is exactly the same each time, and we believe all electrons are identical, we still get a distribution of different values. We don't necessarily get one dot. In fact, we saw for sure we didn't get one dot. We got dots all over the place. And when we added them up, it was much like looking at a billboard. When you're too close, it's just dots. When you get back, you see the big picture if you have a lot of dots, and then you see that it looks like a wave. And keep in mind that this is in a hypothetical perfect experiment. It's of course not possible to do a perfect experiment, but it's possible to get very close to a perfect experiment with some kinds of setups if you're careful. And even then you get a distribution of results which is just far, far greater than any uncertainty in whatever you set up. And so that looks like there's something else at play. And you might think, well, maybe there's noise. Maybe there's some kind of thing that we don't perceive. And it's there like road noise. You only notice its absence when you go camping, but you don't tend to notice it when it's there, even though it's always there. So maybe everywhere when we're shooting these electrons and photons, there's some kind of noise or something else around. And if we were smarter and we figured out what that source was, what was jiggering things around, then we might be able to get rid of it. And then we might not have this theory of quantum mechanics. We would have a theory where we could measure things the way we want to and so forth and so on. And in fact, it seems like that's not the case, that quantum mechanics really says that this probability is the nature of nature and not the result of an incomplete theory by leaving out something hidden that we just couldn't figure out. One of the biggest luminaries so far in physics didn't like this theory. Einstein famously said, "God does not play dice with the universe." Keep in mind, though, that very bright people can be wrong about things. Linus Pauling, who was one of the brightest guys so far in chemistry, had a theory that vitamin C in huge doses would prevent prostate cancer, and that was disproven, even though he believed it ardently. And in this case, apparently even Einstein was incorrect. In fact, it seems like there's nothing but probability. There is nothing else. For example, radioactive decay doesn't depend on pressure, temperature, or anything else that's been explored to any appreciable degree. That's why we can use it to date things and figure out how old something is and so forth and so on. And we believe that all the nuclei are identical. They all have the same number of protons and neutrons, and there they are in the sample. And yet, all we can know is the half-life, which is the time, for example, for half the sample atomic nuclei to decay away into some other element. And for carbon-14, the half-life is about 5,800 years, which makes it convenient for lots of measurements of things that have been around since humans have been around, but not too useful for something that might be extremely old, because then there's no carbon-14 left, and so when you try to count it, you just see nothing. And you can say it has to be older than this, but you can't really narrow it down too much. But if we look in our identical sample and we watch them, there is no way we can tell which particular nucleus out of all the identical set is going to decay. We can't beforehand make any kind of experiment that's going to tell us that. All we can say is that in 5,800 years, there are going to be half as many as there were today. And so this means that really probability is the whole thing when it comes to something like this. So there are some postulates of quantum mechanics. We need to understand them because we need to have this new theory down pat. We need to know what assumptions it's making. And these postulates form the basis for all of our understanding and for all the detailed calculations that we might undertake. The first postulate is this: at any time, the state of a quantum system is described as fully as possible by the wave function psi, which depends on the coordinates of all the particles that make up the system. These could be the electrons and the nucleus in an atom, or something bigger like a molecule. But in any case, if we know psi, we know everything that it is possible to know about the system. And what that means, comment 1, since the wave function contains all that we can know, it follows that most of the time we do not know the wave function. Because in order to know the wave function, we would have to be making lots and lots of very clever measurements, and usually we don't. So usually we just know the dog's in the yard, but we don't know exactly where it is. So if we say we know the wave function of a system, we're making a very, very strong assertion. Comment 2, we're often interested in wave functions for quantum systems that are not changing in time. Like, for example, the properties of an isolated atom or an isolated molecule. And in that case, we use a lowercase psi to denote the wave function. But in some cases, we might be interested in a time-dependent phenomenon, and then we use an uppercase psi, and the problem is they look very similar. Usually you put like a serif on the top to indicate that you're using the uppercase psi, and usually you set time apart as a separate variable. So time is an input to the wave function. You have to know the time to calculate the wave function. And you write it as I've written on the bottom of slide 52 here. So the question is, how can we suppose that the particles, whatever they are, have exact positions, R1, R2, R3, and so on, when a couple of slides ago we just decided that there's an uncertainty in the position of any quantum particle? Isn't this kind of using sort of bad logic here to be assuming this? And the answer is no. It's only with respect to measurement that we have to worry about the uncertainty principle. And even then, it's only for joint measurement of something like position and momentum along the same coordinate axis, x position, x momentum. The variables here, the x, y, z coordinates of all the particles, are better viewed just as simple parameters on which the wave function depends. And once we've calculated the wave function, then we can use it to describe all our measurements that we're going to make, and magically everything comes out just hunky-dory. Postulate 2 makes an assertion about probability. It says now what this wave function means. The probability of measuring the position of a quantum particle at some position, let's say x naught, within some small region, dx, small enough that the wave function doesn't change value very much over the small region, is given by psi star psi dx, or modulus psi squared dx for a one-dimensional system. For a three-dimensional system, we have to integrate over all the spatial variables dx, dy, dz, or in polar coordinates dr, d theta, d phi. And in any case, now we have psi r naught squared times dv. Some books use d tau. I prefer dv because it reminds me that it's volume. So our first comment is, what is the asterisk? What is the psi star? The answer is that the asterisk denotes the complex conjugate, because the wave function is often complex. Now at first blush that seems like that might be a problem, because you're saying that this thing that's associated with a particle is got an imaginary part to it. But in fact, not really, because I can write down a simple algebraic equation, let's say x squared plus 1 is equal to 0, and that has a solution, but it has an imaginary part. So if I just say, well, I don't want to have any imaginary numbers at the in the wave function, it might be like algebra. I won't have a theory of rooting polynomials or anything left over in my theory. So we accept this, but of course we realize probability is real, and that's exactly why we take the complex conjugate. So if you're given a complex number, z equals x, x is called the real part, plus iy, y is called the imaginary part, then the complex conjugate is obtained by just changing the sign of the imaginary part. You can think of a complex number having an x part and a y part, and the complex conjugate, the x part's the same, but the y part is reflected to the other side. So if it's up here, it goes down. If it's down here, it goes up. And you just do that wherever you see I, mechanically. And it's very straightforward to do. So it's not a big deal in terms of calculation. And if you then work out what z star z is, or absolute z squared, or the modulus squared, you'll find that it's x squared plus y squared, because you have to recall that I squared is equal to minus 1. And that's exactly what we want, because then it's a real positive number, and it corresponds to the length of something. And usually when you have the length of something, that means you're going to be able to add them up, because length adds. And in our case, it's going to be probabilities that are going to have to add up, and they're going to have to add up to 1. Comment 2. The probability of finding the particle somewhere in the universe should be 100%. That is, the particle shouldn't disappear. Now, in some cases, particles are annihilated and they turn into other things, but we aren't going to consider those cases in chemistry. Those are for physics. In terms of us, if we have an electron, the chance of finding it somewhere has to be 100%, at least in principle. And that means that there's another constraint on the wave function. The wave function should be normalized. That is, the integral from minus infinity to infinity of psi of x squared dx should be equal to 1. And that means that, of course, psi of x, whatever it is, has to be a function that we can integrate. And it'll turn out that it should also be a function that we can differentiate as well, so we can figure out where things are going in time and so forth. And that means that psi of x is really, in mathematical terms, a very well-behaved function. It's not any exotic mathematical function that would cause us problems. Of course, we put these limits on the integral plus and minus infinity, and we do not think the universe is infinite, or rather, we think the universe is not infinite. But the math that we do is much easier when we make the limits infinity. And this is often true in all kinds of fields, where if you have an infinite sheet of charge, it's very easy to calculate the electric field and so forth. And if it's a finite sheet, it's much harder. There are terms to subtract. And if there's a funny shaped sheet, it's really, really hard, and it doesn't teach you anything necessarily different. And so just to get the principle down, you usually take a simple case, and often it's infinity. So we're going to assume that the universe is infinite. That won't make any difference for our calculations. Postulate 3, for every observable property that we can measure, energy, linear momentum, position, angular momentum, there's a new player in the game. It's a linear Hermitian operator that acts on the wave function. So now this is a new object that many of you may not be acquainted with, so I want to take a little bit of time and explain what's going on. An operator is like the big brother of a function. When I think of a function, I think the function grabs an input number and then returns a function value. So it grabs a number and it gives back a number. An operator, so like y equals f of x, for example. An operator takes in a function, the whole thing, and then gives a new function. And there are things that take in operators and give new operators, and so you can keep going. But terms of this course, we don't need those other objects. So I've written here omega with a hat takes in the function f of x and returns the function g of x. In this course, operators are going to be like gentlemen in the 1950s. They are not going to show up without a hat. And usually we just omit the extra set of parentheses. We keep the hat on so we know we're talking about an operator and not just a number or something else. And we simply write omega to the left of the function, always to the left, because it's acting on it to the right. Omega acting on f gives g. And operators can be as simple as just multiplying by a function, by x, or even a constant, because that gives a new function, or even multiplying by 1, so we get the same function back. That's still an operation. So here I've written x hat, the operator x hat, operating on f, gives the variable x without the hat times f, and that's the new function g. So if f is x, then x hat on f is x squared, and so on. Once the operator is done operating, the result is a new function which just has variables, and which might be the same. So one of the things you're supposed to do in quantum mechanics when you see an equation with an operator in it is you're supposed to let the operator do its work and then get back to just functions that you can differentiate and integrate and so forth. So that's the goal. Don't leave the operator hanging around unless you have to. Comment 4, operators have units. Multiplying by x is going to add length units to the new function. And in chemistry, we have to be careful about units. We can't just be multiplying by things and not know what the units are. We have to make sure we get the right units, whether it's energy or momentum or position. This leads to practice problem 5, which is the following. Does a wave function have units? And if so, what are they? Well, let's go back to what the wave function was. We know the integral of the wave function squared represents a probability. Probability is a ratio and has no units. So we wrote for a normalized wave function, the integral of psi star psi is equal to 1. But the integral is against dx, and dx is like x. It has units of length. And therefore, psi star psi, whatever it is, must have units of inverse length, or length to the minus 1. And therefore, since there's two of those guys, and changing the sign of the imaginary part doesn't change the units, psi itself must have units of length to the minus 1/2 power, or 1 over the square root of length. For a three-dimensional wave function, psi has to have units of length to the minus 3/2 power. The expectation value, or average value of any observable, once you know the wave function, is given by an integral of a sandwich with psi star, the operator, and psi on dx. This is for a one-dimensional problem. The expectation value is usually denoted with brackets around the thing, which means an average value, or the value we expect, with a very, very large number of measurements. But no single measurement need ever return the expectation value. For example, if I flip an unbiased coin and I count 1 every time it comes up heads, and I count 0 every time it comes up tails, then the expectation value, if I make a very large number of tosses, is 1/2. But we never get 1/2 in any of the measurements we do. We either get 0 or 1. Here's a challenge, if you're interested, a little bit harder. What's the expectation value for throwing a pair of dice a large number of times? If you can do that kind of problem, you may have a history in playing craps or other gambling games. Postulate 4, the only possible result of a perfect measurement is one of the eigenvalues of the operator corresponding to the measured observable. That's quite a mouthful. What does that mean? Well, eigenfunctions and eigenvalues are central mathematical objects in the theory, and that's one reason why you ought to take math courses up to and including linear algebra, so that you can learn about these things without having to learn them on the fly while you're also trying to learn something else about the subject. An eigenfunction is a function which the operator returns unchanged, except for multiplication by a number with units. So first of all, here's the form of the eigenvalue equation. I've written here omega hat on f gives little omega, which is a number with units, on f. But the main thing is that f is the same function, and omega is a constant called the eigenvalue. And what we want to do in quantum mechanics often is, given an operator, we want to know what its eigenfunctions are, because the result of a measurement is always one of the eigenvalues of the operator. And if we don't know its eigenfunctions, we can't calculate its eigenvalues very easily. So to go back to the die, suppose we don't know anything about it. We might think, well, we could get 1.5 for an answer, because we don't know how it's shaped. We don't know what it is. But in fact, if we look at it, it's got numbers, integers, 1, 2, 3, 4, 5, 6. Those are the only values you can get by tossing a die onto a table. You can't get something else. And just knowing that those are the only 6 possibilities that you can have is knowing a ton compared to not knowing anything or thinking they can be whatever values you might dream up. So given an operator, what we have to do, we often have the task of finding all the possible functions f and all the possible values omega that make the eigenvalue equation true. And in mathematics, the set of eigenvalues is called the eigenvalue spectrum. That's just for you aficionados. Let's do a practice problem. Let's consider the derivative operator d by dx. What's the set of eigenfunctions and eigenvalues for this operator? Well, we set the operator to the left of the function's unknown, and the eigenvalue's unknown. So we're just going to say the derivative of f is equal to z times f. And this eigenvalue equation then, in this case, amounts to solving a first-order differential equation. And my advice is that's another very good math course to take so that you know how to do it. In this case, it's fairly easy to do. We separate variables, and we write df upon f is equal to z dx, and then we put integrals on both sides, and then we realize that z is a constant, the eigenvalue, that does not depend on x, and therefore we can move z on the outside of the integral. We can look up the antiderivatives, use Mathematica if you've had Chem 5 to do the integrals, or you can actually put an equation like that into integrals.com online, and it'll solve it for you. And well, you'll find that the natural log of f is equal to zx plus some constant, because this is an indefinite integral. And if we exponentiate both sides, we find the function f of x is equal to e to the zx plus c. We can factor that out as e to the zx times e to the c. And then we can let e to the c be some constant, k e to the zx. And as a check, we can always substitute our solution into the original equation and see that it satisfies it. In fact, when I was doing differential equations, one of the most powerful methods was guessing. You guess the solution, put it back in, and see if it works out. And that can often be quicker than to try to do it the forward way. So here, let's do this. The derivative of f of x is the derivative of k e to the zx. And that's k times the derivative of e to the zx. Even I know how to do the derivative of z to the ex, of e to the zx rather. That's kz e to the zx, and that's just z times f. So we've shown that the operator operating on f gives a number z that doesn't depend on x times f of x. That's exactly what we have to do. So the eigenfunction of the derivative operator is the exponential function, and the eigenvalue can be any complex number z, as long as it's a constant. And the reason why, when you solve differential equations, that the exponential function occurs everywhere in these solutions of these equations is because it's an eigenfunction of the derivative operator. One comment, the derivative operator is linear, the integration operator is linear, and by linear I mean this. The derivative of alpha f plus beta g is alpha times the derivative of f plus beta times the derivative of g for any functions a, f and g, and any constants alpha and beta. However, the derivative operator is not Hermitian, and to go back to how we were going to characterize observables, the idea was we had to have a linear Hermitian operator. Now we know what linear means. We have to figure out what Hermitian means, and it has to satisfy this following relationship. The integral of f star omega hat g is equal to the complex conjugate of the integral of g star omega hat f. So we put a star and we swap the order of the functions. If it follows that, it's Hermitian. And here, f and g are any reasonable functions that are integrable in the usual sense. Okay, that's quite a bit for today. So we're going to take a break and come back tomorrow, and we're going to pick it up on what Hermitian operators are, cover a couple more postulates in quantum mechanics, and then do a few interesting problems.